This video is brought to you by Astronics Test Systems and the Freedom brand of communications system analyzers. The topic of this video is NXDN and dPMR radio test. What skills can you expect to gain from this presentation? We will study an overview of the history of the NXDN and dPMR standards, an overview of the AMBE vocoder and its conversion of analog to digital speech, key measurements and their limit values, how to configure the Freedom R8000 series of communications analyzers in NXDN and dPMR mode. How is this presentation structured? First, hear about a customer who used his skills to test a portable NXDN radio in digital mode using his radio test equipment. Next, review the basics of NXDN and dPMR radio systems and take a quick peek under the hood at the digital protocol that makes it possible. Finally, discover how to quickly and simply set up your Freedom test equipment to perform both transmit and receive tests in NXDN or dPMR digital mode. Could these skills help you save time and money? That's exactly what happened to Mike at a construction company in Canada. A radio system user was not able to reach his supervisor on the emergency channel during a routine radio test. This user's health and safety were at risk until the issue was resolved. Mike needed to find the problem and fix it quickly. Using his Freedom R8100 analyzer, he tested the NXDN signal being transmitted by the radio on the emergency channel. He discovered that the radio's programming was not correct. The RAN code for the channel had been inadvertently mistyped. He was able to reprogram the radio and get the user back on the air in a matter of minutes. He was pleased that his test equipment could provide insight into the digital performance of the radio. Without this capability, Mike would have spent time testing the radio's hardware and finally driving to the site to identify the source of the problem. Mike's understanding of the NXDN radio system and his test equipment helped him analyze and respond to this situation in record time. What is NXDN and how does it work? Why do we test radios? First of all, for preventative maintenance and periodic testing of radio fleets. Second, to maintain optimal performance of the radios. Third, to control potential interference. And finally, to provide the user with confidence that the radios are operating efficiently, especially in marginal conditions. The NXDN standard was developed by the NXDN Forum, which is a collaboration started by Kenwood and ICOM and joined by a number of other industry stakeholders. Eventually, the forum collaborated with the dPMR Association and made the low narrowband capabilities available to them. Later developments included Type C and Type D trunking. Type C includes a control channel. Type D uses in-band signaling instead of using a dedicated control channel. The Type C trunking mode will be covered in a different presentation. NXDN employs a frequency division multiple access or FDMA architecture and a 4-level frequency shift keying digital modulation scheme. There are 2 data rates of 9600 baud in wideband channels and 4800 baud in narrowband channels. dPMR is 4800 baud narrowband only. AMBE +2 vocoder is employed for the digital speech at full rate or half rate, depending on whether you're in wide or narrow bandwidth channels respectively. The standard contains a digital scrambling mode that's built in. but also allows for the use of AES or DES encryption. dPMR is used in 12.5 kilohertz channels, or wideband, or 6.25 kilohertz channels, narrowband. The dPMR standards allows only 6.25 or narrow bandwidth. In Europe, dPMR 446 is an unlicensed 400 MHz band allocated for NXDN used for public walkie-talkie deployment. The RF power, however, is limited to half a watt. The NXDN standard defines 3 modes of operation. Mode 1 enables local peer-to-peer communication without repeaters or infrastructure. Mode 2 extends the range at a single site or multiple interconnected sites using a single channel by the use of repeaters and other infrastructure such as IP interconnects. Mode 3 implements full multi-channel, multi-site trunked radio networks. This mode is outside the scope of this presentation. This presentation focuses on the 2 conventional modes of operation. Again, in Mode 1, portable and mobile radios communicate directly with each other using a single transmit-receive frequency. This is often referred to as simplex or talk-around operation. A user's signal is only received by others who are within a limited distance. Mode 2 is when portables and mobile radios use a frequency pair. They transmit on one frequency, which is received by the repeater and simultaneously rebroadcast or repeated on another frequency so that it can be received by anyone who is within the wider range of the repeater's tower. Everyone on the system uses the same frequency pair to communicate. The range can be even further extended by linking multiple repeaters together to cover a large geographical area. By connecting the sites by IP using the internet or other private data networks, when a user transmits into the system, the signal is repeated across all sites, potentially anywhere in the world. Each site may have its own frequency pair, but when the repeaters are linked, all pairs are used at the same time for a single conversation. The NXDN and dPMR protocols encode digital information by modulating an RF carrier in such a fashion that data can be extracted from the signal at the receiving end. NXDN and dPMR employ 4-level frequency shift keying digital modulation scheme. This means that the radio is shifting the frequency of the RF carrier. The frequency is shifted above and below the center frequency and shifted by 2 separate amounts. The size of the shift depends on the available space or bandwidth of the channel. If the channel is wideband or 12.5 kilohertz, the signal is shifted by 2400 hertz or 800 hertz, either above or below the center frequency. If the channel is narrowband or 6.25 kilohertz wide, the signal is shifted by 1050 hertz or 350 hertz, either above or below the center frequency. Note, dPMR only uses the narrowband channel. Since the signal has 4 possible values, it can send 2 bits at a time, 00, 01, 10, or 11. After sending those 2 bits, the next 2 bits are sent by shifting to the appropriate frequency. In a wideband channel, 9,600 bits can be sent every second. In a narrowband channel, there is room for 4,800 bits every second. This is also called baud, bits per second. How do we turn voice into digital bits and then back to voice? That's the job of the vocoder, or voice encoder decoder. The vocoder takes analog voice and encodes it using a complex algorithm that breaks down the human voice using an ingenious model of human speech. The first part of the process is an analog to digital conversion, which turns the voltage levels into their digital values. Next, the digital data is compressed using the proprietary AMBE+2 vocoder developed by DVSI. Forward error correction bits are then applied to the data so that it can be perfectly recovered even with a few bit errors during the transmission process. The resulting bit stream is then applied to the 4FSK modulator and is transmitted. The receiving signal operates in reverse and converts the digital back into analog speech. If the radios are being used to send digital data instead of voice, the vocoder can be bypassed completely and digital data is passed directly to the modulator and recovered directly from the demodulator. There are two versions of the vocoder. The full rate vocoder is used in wideband channels and uses 7,200 bits per second. Less compression means better audio quality. The half-rate vocoder is used in narrowband channels and uses 3,600 bits per second. More compression means reduced audio quality. How can the communication be kept secure from eavesdropping? NXDN and dPMR standards include several mechanisms to encrypt and decrypt the data being transmitted. NXDN and DMR protocols have a built-in scrambling capability. This is a basic encryption scheme and is not extremely secure, relatively speaking. To provide more robust security, the standard allows AES or DES encryption to be used. Note, the voice loopback function on the R8100 works regardless of the encryption. We will cover voice loopback later on in this presentation. More advanced features of the standards, such as those listed here, are beyond the scope of this presentation. More information is available online and in the standards documents. With all of this technical background regarding NXDN and dPMR standards and protocols, the question still remains: how can the radio technician test a digital NXDN or dPMR radio, and what measurements and information can be exposed for testing, aligning, and troubleshooting radios? The NXDN test mode is a software option which has been available for many years on the Freedom R8000 series communication analyzers. It can be easily installed in the field on your R8000A or B or C models, R8100, R8600, or the recently introduced R8200, which incorporates a single-port VNA into our full-featured LMR test platform. The same is true for the dPMR test option. This option provides the capability to test, receive, and transmit functionalities of mobile and portable radios in Mode 1 and Mode 2 conventional modes. If you would like to test a radio in Type C trunking mode by simulating a base station, contact us about the option which is available. However, we will not cover that option in this presentation. Once the instrument is changed from analog to NXDN mode, which by the way is nearly instantaneous, and while in monitor mode there are only two parameters that are needed to start measuring the output of the radio. First, we need to tell the instrument the operating frequency of the radio. A few keystrokes later, we are able to see the signal when we key the radio. We can copy this frequency to the generator with a single key press to save ourselves times later. If the baud rate setting is correct, no further setup is required. Otherwise, a couple key presses will switch between the two data rates. Just that quickly, we are ready to test the transmitter of the radio. Connect the radio to the RF input-output port. Turn on the radio, select it on the proper channel, and key the radio. Let's take a closer look at the information that is provided on a single screen without having to fumble through multiple menus and windows. Now we are looking at the measurements that are being made live on the NXDN input signal. In the RF zone in the upper left-hand corner of the screen, we have three basic RF measurements. We have the RF power in dBm or watts. We have the carrier frequency error and the total measured deviation. In the NXDN zone, which is the lower left-hand corner of the screen, we have four pieces of information about the digital signal. We have the TX radio access number ID code. This is the RAN code. It's an ID that identifies a specific group of users. Multiple users or multiple groups can use the same channel without hearing each other's conversations. Of course, this means that sometimes users will have to wait before transmitting if the channel is busy. This decoded RAN code can also be copied to the generator with the push of a button, which again will save time when testing the receive of the radio. The next measurement is the symbol deviation. The ideal value for a 4800 baud or narrowband signal is 1050 Hz, and 2400 Hz is the ideal value for the 9600 baud or wideband channel. Next, we see the modulation fidelity. This is an excellent measurement of the quality of the modulation of the signal. It indicates how close to ideal the symbols are. We'll look at the eye diagram in a bit, which shows us visually how clean the signal is. The next measurement is the transmit bit error rate. Note that the radio must be modulating the signal with one of the selectable test patterns for a correct bit error rate reading. Some of these predefined patterns from the standard are the 1031 Hz tone, the 0.153 calibration tone, and the 511, which is a separately defined standard. On some radios, this may be initiated by a keyboard sequence on the keypad. On others, however, you will have to use the tuner software from the radio manufacturer to have the radio transmit these signals. Since the radio is connected directly to the instrument, we're receiving full power. Bit error rate should be 0 unless there's a serious problem with the radio's hardware or firmware. If the test patterns don't match, you will get a high bit error rate. So if you get a high bit error rate, first verify that the correct pattern is being transmitted and we're comparing to the correct pattern on the receive side. There are several graphical displays that are selectable. We have the spectrum analyzer, the bar charts, or the eye diagram. Let's look at the eye diagram for a minute. The horizontal axis is time. The vertical axis is deviation. The center frequency is an imaginary horizontal line across the middle. The four convergence points, where you can see the different traces aligning, are the four symbols. There are two above the center and two below. The eye diagram is showing us how the signal's deviation is changing over time from one symbol to the next. We see the trajectories as the signal's frequency shifts from one level to the next. Since we are connected directly to the radio, the signal is strong and we should have large open spaces or eyes between the symbols. If we measure a signal received over the air, the signal will be much lower. As the power decreases, incoming power decreases, we will see that these trajectories start to wander from their ideal positions and these eyes will appear to close. Remember, modulation fidelity is the actual measured value of the quality of the modulation. This is a value that can be tested and compared to the specifications in the standard. A quick note about bit error rate, or BER. The bit error rate will start at 0 until one of the trajectories wanders more than halfway towards a different symbol than the one that was sent. Only then will a bit error occur. And since there is forward error correction in the protocol, it will take a number of bit errors before the bit error rate measurement actually rises above 0. And so the modulation fidelity will already be showing us problems long before the bit error rate indicates an issue. Bit error rate is only useful when measuring at the very edges of the radio coverage. And remember that the quality of a digital signal behaves very differently from an analog signal. Analog signal quality fades in a smooth way at the edge of your coverage area. Digital signals are crystal clear much further out, but once the bit errors start, then the quality degrades very sharply for small changes in signal strength. Keep this in mind when looking at weak signals over the air, whether you're using a radio or a repeater. A few more words about bit error rate and test patterns. The instrument calculates bit error rate by comparing the received value of the pattern that is actually selected. The radio must be made to transmit the correct pattern, and the instrument must be comparing it to the same pattern. The bit error rate measurement must be started to tell the instrument to begin comparing the received values with the expected data. Now let's switch to testing the radio's receiver. Setting up the instrument to transmit a signal to the radio is just as simple. We switch to the generate mode, which automatically starts transmitting an unmodulated RF signal. If we copied the frequency from the monitor mode earlier and the RAN value, the only remaining task is to tell the instrument to modulate the signal with an NXDN test pattern. The default test pattern is the 1031 Hz tone. We set the modulation mode to continuous. Before we start the modulation, the radio should have indicated that the channel was busy when it sees the RF carrier. Once the modulation starts, if the RAN matches the RAN code of the instrument matches the RAN code in the radio, the 1031 Hz tone will be heard coming from the radio speaker. Try changing the RAN number to see if the radio squelches the output. From here, we can decrease the RF output power of the instrument until this tone starts to break up. Or if we use the radio manufacturer's tuner software, we can have the software tell us the measured bit error rate at the radio. When the bit error rate measured at the radio reaches 5%, the RF level output of the instrument is the sensitivity, the digital sensitivity of the radio receiver. The standards define several other test patterns, but only the 1031 Hz pattern will produce an audio output on the radio. The voice loopback feature enables the operator to record a message and play it back to the radio. The talk around or simplex channel in the radio is required. This test is a full round-trip test of the radio. It tests all of the following in one test: the microphone, the audio input circuitry, the vocoder encode capability, the encryption, if any, the transmitter, then back into the receiver, decryption, if any, vocoder decode, audio output circuitry, and finally the speaker. Again, a full round-trip test of the radio. The instrument records the signal it receives once the squelch opens on the instrument, and the duration can be configured. Only the last part of the transmission is kept when the radio is unkeyed. Once the instrument squelch closes, the instrument automatically switches to the generate mode and transmits a signal into the radio. Once this is complete, the instrument goes back to monitor mode and waits for the squelch to open to start recording again. If the signal has encryption, the radio's encryption-decryption will process the data without having to load encryption keys into the instrument. The instrument has no decryption functionality, so no one can compromise your system encryption keys by having access to your instrument. In dPMR mode, the screen is nearly identical in both monitor and generate modes. Again, you can see the RF power displayed in dBm or watts, the carrier frequency error, the symbol deviation in the NXDN zone, the modulation fidelity, and the bit error rate test, and of course the various graphical displays. The only small differences between the NXDN and dPMR test modes are in the generate mode. In the dPMR mode, there is a selectable filter to account for two different standards in the dPMR within the dPMR Association standards, the ETSI or the PDR filter. The other change is related to the test patterns that are available. The dPMR standard has a slightly different list of patterns than the NXDN standard. In all other respects, the instrument behaves the same in both modes. For additional information and step-by-step instructions, please find the following app note titled Testing Kenwood and ICOM Radios on the R8000 Series Communications System Analyzer, which is located in a document library on the Freedom website. Freedom Communications System Analyzers have an optional feature called Autotune, which is an automated test suite for the Kenwood NX radios. You will find more information on our website and in the Autotune user guide shown here. Autotune allows the instrument to take control of the radio through its programming interface and performs the manufacturer's test and alignment procedures as documented in the radio service manual. Once the connections are made to the radio and instrument, the process is fully automatic and greatly reduces the test time and frees up technicians for other tasks such as programming radios, troubleshooting, repairs, and other field work. You've just seen how simple it is to set up the test instrument and test digital NXDN and dPMR radios. The information provided to the user in an NXDN test mode allows rapid troubleshooting and accurate diagnosis of radio or system issues. The Freedom R8000 series of communication systems analyzers provides the right tool for your NXDN and dPMR testing needs. Provides a full suite of NXDN or dPMR transmitter and receiver measurements. The voice Loopback test tests the vocoder, the mic, the speaker, even when encryption is applied. Test results are displayed both in digital and graphical formats, helping you to quickly identify potential problems. And again, we support all industry standard vendor-specific test patterns. Please check our website for information about our products such as data sheets, brochures, operators manuals, user guides, application notes, and other videos. Contact information for our sales and application engineers are on the support page. To schedule a product demonstration or to obtain pricing information, contact your local U.S. manufacturer's representative or international distributor. You can also connect with us through social media channels. On behalf of the Freedom team at Astronics Test Systems, we trust you have found this presentation useful and hope you will reach out to us and let us show you how our expertise, experience, and products can save you time and money as you endeavor to keep radio communications flowing on your system.